Hello everyone, I'm Christoph, I'm with AWS, and what I want to talk about today is indexing blockchains. As you probably know, blockchains are very good at storing data, but not really good at retrieving them. So we'll need some sort of solution for that. There are, of course, a lot of services that provide that. You can always use them, and that's always the first choice, but there might be reasons to build your own indexer. And that's what I'm going to talk about today. And how would you do that if you were using AWS? Now, if you have a very simple data flow, that's what it looks like. We have a mobile client or desktop client, then we have a front end, and then, of course, we have the blockchain, and we're pulling data from off of it. Now, the easiest way to do that, and that's what you normally start out with, would be to query a smart contract directly. You can just issue RPC calls against the node, get the data, and then display it. There's all kinds of problems with it. You're restricted to individual RPC calls. You have to do them one by one. It's very resource intensive for rich queries because you're actually querying the node for every single bit of data. So it's really not a good way to do it. So we'll just skip over that. Second one is, of course, use an existing indexer or one of the open source frameworks. Something like the Graph, that's probably the most well-known one. Good thing about that is you have full control over the mapping. Or if you're using one of the existing providers, you can just basically use what they are providing and don't have to care about your own infrastructure provisioning, infrastructure deployment, maintenance, and all that. Every once in a while, you might get into the situation that that data isn't enough or it isn't good enough for some reason. So you really want to go and build your own indexer. What are the problems with using the existing ones? First of all, the indexer usually pulls the data via RPC still. So while you have an indexer in between your blockchain node and your front end, the indexer itself, of course, pulls data via RPC from the nodes and then provides it in a somewhat better and easier to query format for you for the front end. But still, we have these RPC calls, and if you've ever tried to do a backfill via RPC calls, that can be very, very slow and can take a lot of time. Also, you have a fairly late transformation in the game. So you're extracting data from the blockchain, and normally, because the indexer does the extraction and the transformation all in one, you basically, whenever you change the transformation, you want to try something new, you basically have to re-index the entire blockchain again. And again, if it's mainnet, that's a fairly long time. We'll come to that a bit later. That's transformation changes require re-indexing of the whole chain, and then late transformation is fairly late in this ETL process. We do the transformation, but we could possibly move it much closer to the actual node to get it quicker. Each one of these three issues, one by one. This is a normal architecture. Again, the blockchain indexer is pulling the data from the blockchain node. Ideally, what we'd like to have, if we want to have an ideal unidirectional ETL flow, extraction from the node to the indexer and then to your front end or middleware, we don't want to have this pull component here, but rather we would like to have the node pushing the data into our indexer. That wasn't available for the longest time. Nowadays it is. And what we're trying to use here is the reth Ethereum client, the Rust Ethereum client, that does provide a means to actually have the node push data into a user-defined sink so that you can use that data more or less immediately. Transformation, excuse me, usually happens fairly late in the process. There is a tendency to move that earlier to where the data is actually generated, to the node. I can highly recommend this blog post. That's not by me, it's by Andrew Hong. He outlines this whole graphic, that's also by him, and it's a fairly good read, so I highly recommend it. But that's also what we're trying to do in the architecture later, move that closer to the node. And finally, the last one, if your transformation changes, you want to make sure that you don't have to re-index the full blockchain, which we would normally do because the extraction and the transformation is really one process. What we want to do instead is have the extraction part getting the data from the blockchain, store it somewhere, and then have the transformation part that only uses that storage instead of going back to the full node. So that's what we're trying to build here. We want to build our own indexer, maintain full control over the mapping, of course, over the transformation, want to have that unidirectional data flow from node to indexer to front end, early transformation if we want to, and transformation independent of the extraction part. Now, if you do want to do indexing, there's one part I need to mention. Of course, we have the full blockchain sitting there on the node. That's the history that we probably want to have. And then there's also the future, all the blocks that are coming along. And there's really two solutions to that because they have different requirements. If you're looking at the history, that never changes. There won't be any reorgs in the history or anything like that. It's just data there that sits on the node and you need to somehow extract it. And you can possibly do that in parallel because we have block numbers, so we can always order that later. And we can just, I don't know, saturate the node with RPC queries, get all the data as quickly as we possibly can, store it in our intermediate storage, and then transform it. So that's one requirement. For the future blocks, of course, we need to be reorg aware. So blocks can possibly be invalidated or disappear if there's a reorg. And our solution must be aware of that. Otherwise, the data isn't right. So two different requirements. Excuse me, two different solutions for it. I'm going to go through that architecture, what it looks like. First, I said we want to have the intermediate storage where we extract all the data to so that we can then transform it. What we're using here is Kafka. At AWS, we have a managed Kafka service that makes it fairly easy to set up a Kafka queue. If you've ever tried to do it manually, it's a bit of a nightmare. It's fairly complex. With the managed service, it's fairly easy to do, so that's what we're using. This is what where our data will be sitting indefinitely. So we'll extract it from the node, store it there. It sits there, and then whenever we do transformation, we'll base it off of that. First thing then, the backfill. We have a blockchain node. In this case, I'm using Cryo, which is an extraction utility that Paradigm made. It's a public GitHub repository. You can just download it, and it's really, really fast. It saturates a node when it tries to extract the data. So don't try that with a public blockchain service. It should be your own node, but because it really sends many requests to the node. But by that, it's fairly fast to extract all the data. And what you're getting is a file-based data that sits on your EC2 instance in that case, and then we can push it over to Kafka. That's for the backfilling part. Once we have that, we have all the historical data in our Kafka. Now we want to make sure that the future data gets into Kafka as well. For that, we're using, or I'm using the reth Ethereum client that has these so-called execution extensions, which is, in a somewhat simplified way, I'd say, a plugin mechanism where you can write plugins in Rust that are directly compiled into the node and basically instruct the node to, whenever there's a new block, to send that data to not only its internal database, but somewhere else too. In our case, send it to Kafka. This is just a very, very small piece of what it looks like, but you can see it's a fairly elegant solution, I'd say, because the execution extension gets these notifications. If there's a new, if there are new blocks, it gets this process committed chain. If there's a reorg, it gets this reverted chain and the new committed chain. And if there's a revert, it gets this reverted chain. So you always know what new blocks are there or if there's a reorg. So it's reorg aware. That's really what we need. Right. And then, of course, because it's written in Rust, possibly you can also do transformation here already if you were so inclined. I haven't done that here. The only thing that I'm doing is really extracting the data and writing it more or less raw into Kafka, because I wanted to compile the node once and then have it running and never touch it again, more or less, and then have all the transformation on Kafka. So that's the next part then. Now we have all the data sitting here. Now we want to transform it. We want to have custom sinks for it. So the first one that I want to, and that I'm going to show later, is extracting specific data. For example, I've chosen the CryptoPunk transfers and the USDC Uniswap swaps. Extract that data from Kafka and then write it into a database. This is just a relational database. Of course, it can be whatever you want, because with this Apache Flink, what we are having there is really Java code that runs and that can do the transformation for you, and that's what it does for me. So in this case, we have this custom sink that accepts all the data, and then, of course, our front end will only ever query that, because that's where the data is in properly transformed format. And, oh yeah, that's what it looks like. This is Java code, so don't have to read through the whole thing, but basically what we're doing here is first block here, filtering for a particular contract, the Punks contract in this case, and filtering for particular events, and then using those events and basically write them into the database. Each event is one record in the database with block number and everything in between. So that's what the Flink code looks like. And of course, because it's Kafka, we can have many independent consumers running on top of that Kafka queue that are really, one starts, extracts all the Punk transfers, the other one starts, extracts all the Uniswap transfers, and they don't interfere with each other, nor do they change the data on Kafka. The data in Kafka is always there as a single source of truth, if you will. And that's it really for the simplest part. I do want to mention one other custom sink that you can implement, which is called S3 delivery via our Amazon Data Firehouse, which basically takes the data as they come along and stores them in Packet file format in S3. So this is really the long-term storage if you ever want it. It just can sit in S3 and then S3 Glacier for the really long-term storage forever at low cost. In Kafka, of course, I've now indexed mainnet, and that is about, I think, 8 or 9 terabyte or so of data sitting in Kafka, which is a lot, to be honest. So at some point, you'll need to decide on how long you want to keep it in Kafka, but for now, it's of course just all in there. So that's basically the architecture how you can build it on AWS. If you then look at it from the ETL perspective, now we have a properly separated concerns, if you will. We have the extraction part, we have the transform part, and then, well, load part, we basically store it in some sink so that we can make use of it. But the important thing, of course, is that we've really separated extraction from transformation, because the extraction is really, well, it takes a long time to do. Transformation is much, much quicker. So we can add new transformations without doing the whole extraction every single time. So that's the really nice property of this whole thing. So just timing-wise, to give you an idea how long that takes, I've indexed mainnet from a fully synced node to around block 22.63 million. Extraction via cryo takes about 9 hours to go through the entire chain and write it into files. Then ingestion into Kafka from that takes about 5 days in its current implementation. But what I've done here is really sequentially ingested it into Kafka. On purpose, I haven't done any kind of multiple partitions, which you could potentially do and parallelize it much more. I haven't done that here. It's really sequential ingestion into Kafka. And then transformation and store CryptoPunk transfers takes about a day or so for the existing chain. Now, just to give you an idea what that does, this whole thing here basically goes through every single log that has been generated since Genesis, extracts the punk transfers from it. As you can imagine, we have 22, 23 million blocks or so, possibly 100 transactions or so, and maybe 2 or 3 logs per transaction. So we are in the billions of log events that are stored in Kafka that we need to go through if you want to do that. So that's why it takes so long. So finally, summary before I can actually show the demo. I've said all that. We've decoupled extraction from transformation, plus we have a unidirectional data flow, no more RPC cores whatsoever. And we have independent consumers, so we can add new consumers as we come along. The really not so nice thing about the whole thing is it's a plethora of languages. So deploying the infrastructure is a CDK script, so TypeScript. The Rust execution extension is Rust, and then the Apache Flink is Java code. So you need to work through all of that, which is a bit of a nightmare, to be honest. But, well, here we are. Now, what does it look like? This is just a very simple front end, obviously based off of the data. Anyone a particular CryptoPunk ID that they're interested in? Between 1 and 9,909?
33.
33. Here we go. Now, what we're doing now, of course, is querying the database, nothing else. That's what it does. And basically what we see here is the minting event and then all the transfers that have happened since then. What we also see is we currently have indexed the database to block 23,830,000 something, which is if you look at the CryptoPunk's Etherscan page, exactly the block that the last punk transfer has happened. So that's exactly what we want to see. And then the final bit, USDC price. That's the V2 Uniswap contract on mainnet for USDC Ethereum transfers. That's the pricing of various swaps that you can see. It's really just showing that there is data to see, and what you also can see is the one is if I'm changing Ether to USDC, that's the Ether price then per USDC, and that's this scale, and then the other one is the other way around if I'm changing back from USDC to Ether, and of course we see that those lines are really mirrored because that's exactly what we're expecting. The prices at the same time should be approximately the same. All right, that's what I wanted to show. I'll switch back to the slides quickly. Because the only thing I wanted to mention is this is our Web3 blog that we have. Hopefully fairly soon, I'm going to publish this whole CDK script on GitHub and write the blog post about it. It isn't ready yet, so that's why I can't show the blog yet. But it will appear on this blog page. So if you want to try it out then and actually deploy all these services and play around with it, this is where it will appear, hopefully fairly soon. I did see we have about 5 minutes left, I think. So if there are any questions, I'm happy to take them. Yeah.
Who's got questions?
Yeah, there's a mic coming.
Thank you. I have a bunch of questions. When you go back to the slide, like what data are you actually ingesting into your system? Is it just receipts? Is it logs? Is it logs and state?
What I'm ingesting is I have 3 different Kafka topics. one for blocks, one for transactions, one for logs. And that's basically what I'm getting there. And the messages themselves are basically JSON records of those three things. So, and then of course for the demo, I'm really only querying the log topic because I don't need the other two.
I don't know if you know, but filtering out the logs for the CryptoPunk transfers takes like 30 seconds on the guest node right now. So it's
I'm fully aware of that. I just wanted to see how long it takes on that architecture.
Yeah. But I think if you create, like we have this new filter index, which
which uses Bloom filters.
Yeah.
That will be much faster, of course. Yeah.
That will be much faster.
All right.
No, I think that was this.
Okay, perfect. I just got the notice that was the last question, unfortunately. But I will be around if there are any more. Thank you.